Today, we're diving into the story of an element so violent, so aggressive, that for decades, chemists just called it an untamable beast. We're talking about fluorine.
Okay, so what's the most dangerous chemical you can think of, right? A lot of people might say something like, I don't know, fuming sulfuric acid. But what if I told you there's an element out there that makes strong acids look kind of tame? An element that can literally set fire to things that should not be able to burn. Well, meet fluorine. If you look at a periodic table, it's sitting all the way up in the top right corner. And in chemistry, that's like the throne room. It makes fluorine the undisputed king of reactivity. It's the most powerful oxidizing agent known to science, a real elemental tyrant. Now, to really get a handle on just how ferocious this stuff is, we have to go back in time. We have to look at the trail of destruction it left, long before anyone even managed to get a pure sample of it. Seriously, this part of the story is, well, it's written in human suffering.
You know, this whole quest started centuries ago. At first, there were just these little hints of its power. Early chemists figured out that this weird mineral, fluorspar, could etch glass when you mixed it with acid. Fast forward to the 1800s, and the race was on to actually isolate the pure element behind it all. And let me tell you, it was a race that went on for 74 years, and it took a very, very heavy toll. Yeah, so many brilliant scientists were hurt or even killed trying to do this that they actually got a nickname, a pretty grim one, the Fluorine Martyrs. I mean, these people were blinded, they were horribly poisoned, they suffered agonizing deaths just trying to corner this chemical beast. It felt like the element itself was fighting back, and for a long time, it was winning. And that's why this was such a huge deal. In 1906, Henri Moissan finally gets the Nobel Prize. And it wasn't for discovering something totally new, it was for finally doing what so many others had failed and died to do. He isolated pure fluorine, and crucially, he survived to tell the tale. Okay, so we've heard the history, but what is it that makes fluorine so uniquely, so violently dangerous? Well, the answer isn't just in those tragic stories. It's in its basic chemistry. This insatiable hunger it has for one specific thing. All right, let's get a little nerdy for a second. Fluorine is the single most electronegative element on the entire periodic table. Now, what does that mean? It's basically a fancy way of saying it is desperately, pathologically greedy for electrons. It doesn't just want to share them or borrow them. Oh no, it violently rips them away from pretty much any other substance it touches. And the results of that electron theft? They're spectacular and absolutely terrifying. Fluorine makes things burst into flames that we think of as non-flammable. Get this, it will react with hydrogen explosively, even when both are frozen solid in the dark. It sets steel on fire, it makes water explode on contact. It will even go after the so-called noble metals, things like platinum and gold that are supposed to be unreactive. You can really see this eagerness to fight when you compare fluorine to its chemical cousins, the other halogens. Just look at this chart. It shows how much energy it takes for these elements to break their own bonds so they can go attack something else. See that line for fluorine, F2? It's way, way above the others. That means it needs way less of a push, way less heat to break apart and just go on a total rampage. It's just itching for a fight in a way that bromine and iodine simply aren't. And this right here, this is why it's so much more sinister than a regular acid burn. The moment fluorine touches the moisture in your skin, in your lungs, it creates hydrofluoric acid. But this is not a surface wound. The fluoride ion doesn't just sit there. No, it soaks deep into your body, through your tissues, destroying cells as it goes. It even leaches the calcium right out of your bones, and this process can continue for days after the initial contact. It's just a relentless deep tissue poison. Okay, so if this stuff is an uncontrollable monster, how on earth are we using it? I mean, it's in everything from pharmaceuticals to nonstick pans to electronics. How did we ever manage to tame this tiger and put it in a cage? Well, the motivation had to be immense, and it was. The first time humanity absolutely positively had to figure out how to handle fluorine on a massive scale was for the Manhattan Project. See, they needed it to make a gas called uranium hexafluoride. That was the only way they could separate the uranium isotopes to build the atomic bomb. So yeah, failure was just not an option. And this is the incredibly clever trick they came up with. It's a process called passivation.
Here's how it works. You take a container made of, say, steel or nickel, and you expose it to fluorine gas. The fluorine instantly attacks the surface. But here's the brilliant part. The layer it creates, a metal fluoride, is super tough and completely unreactive to more fluorine. It's like the fluorine builds its own cage, a perfect, impenetrable prison wall that stops it from eating through the rest of the metal. And that one trick opened the door to all kinds of amazing engineering. The pipes were corroding, okay, plate them with nickel. But what about flexible seals and gaskets that fluorine would just chew through? Well, they had to invent a whole new material just for that problem. And they did. It was called Teflon. Yep, that Teflon, one of the very few things on Earth that can just shrug off a direct attack from fluorine. But even with all these amazing breakthroughs, handling fluorine today still demands an incredible amount of respect and caution. The tiger is in the cage, sure, but you never, ever turn your back on it. When you're working with fluorine, you're not just doing a job, you are constantly prepared for the absolute worst-case scenario. That means first aid, emergency response, everything planned out to the second. These aren't just good ideas. They're the bare minimum you need to stay alive. And the safety rules are non-negotiable. You've got to have constant, powerful ventilation to pull away any leaks. But maybe the most important rule of all is this. You always work with a partner. The buddy system isn't a suggestion. No one, absolutely no one, is ever left alone with fluorine. Ever. The danger is just too fast, too severe for one person to have any chance if something goes wrong. So when you step back and look at it, fluorine is this incredible paradox, isn't it? It's one of the most dangerous things we know how to make. It's responsible for a long, tragic history of death and injury. But at the same time, it was the key to unlocking the atomic age, and it's absolutely essential for modern life, from medicine to materials science. It's both chemistry's greatest weapon and its most terrifying monster. Which really makes you wonder, what are we going to dare to do with it next?